Hello. This is part of the annoying calculation series where we do some of the annoying calculations that one might need for a calculus-based probability and statistics course. This video deals with the binomial distribution. And here's the idea. We have the binomial distribution, and I'll define the density function for it, or the probability mass function as it's sometimes called. I'm going to go ahead and explain the following things. I'm going to explain why the formula works as a distribution, the sums to one. Calculate its moment generating function, which I realize can be used to calculate the mean and the variance, but I'm going to calculate these two from first principles without using the moment generating function. So let's just review what the binomial distribution formula is. And it says that the probability of getting y successes out of n trials is going to be given by n choose y, py 1 minus p to the n minus y. And this is true for y between n and 0. And it's going to be equal to 0 otherwise. Now, I should just give a very, very brief review about what the binomial distribution really is. The idea is that we have n independent trials, and the probability of success in any trial is p. So for example, suppose you take the situation where you have a basketball player, and assuming that the probability of them making a free throw are independent events, and I understand that's open to debate, and let's say someone shoots 70% and they take 10 free throws in a game. You don't want to know what's the probability that they made 8 of them, that they made 7 of them, that they made 6 of them, that they made all of them. And in your course, you're probably given this formula for the binomial distribution, where success is meaning a make, where there p would equal 0.7 and 1 minus p would be 0.3. Now, I'm going to deal with this sort of the nuts and bolts of the distribution itself. And the very first thing I want to do is I want to show that if you take a sum from y equals 0 to n of p of y, that you get 1 as you're supposed to. Now, this isn't that bad at all. And here's the proof. You take p plus 1 minus p, sometimes denoted as q, and you raise it to the nth power. Now, of course, this is going to be 1 to the n, which is 1. Okay, it's not too hard. On the other hand, if we expand by the binomial theorem, what we get is we get n choose 0, p to the 0, 1 minus p to the n, plus n choose 1, p to the first, 1 minus p to the n minus 1, and you just keep going. Let's say n choose k, p to k, 1 minus p to the n minus k. And that just keeps going to n choose n, p to the 0, 1 minus p to the n. And that, of course, is each one of these. Of course, that's by definition the sum of this. By the definition of the way this is written. Okay, so that's fairly straightforward. The binomial distribution is basically the binomial theorem. Now, let's calculate the moment generating function. And I think I screwed that up. What am I? Oh, I see what I'm doing here. I'm doing a triangle instead of a line. That was a, hopefully it doesn't degrade your confidence too much in me here, but now let's go ahead and calculate the moment generating function. Well, let's see. Well, that is by definition the expectation of e to the ty, which is the sum of p of y, e to the ty from y equals 0 to n. Well, let's just add this up. Y equals 0 to n. P of y, remember, is n choose y. P to the y, 1 minus p to the n minus y times e to the ty. Now we use the fact that e to the ty is equal e to the t to the y. And now what I'm going to do with this is I'm going to combine these two, which are both raised to the y power. This is going to be p e to the t, all raised to the y power, 1 minus p to the n minus y. And now by the binomial theorem, then you can see just how useful this is. This is one of the terms, and this is the other term. So this is going to be p e to the t plus 1 minus p, all raised to the nth power. And that is going to be the moment generating function for t. Now notice, I should say note, if you take the first derivative and set it equal to 0, if you know about the moment generating function, that'll be the expectation of y. Let's become calculus students. You're differentiating this with respect to t, so the n comes down. To the n minus 1 power, multiplied by the derivative of the inside with respect to t. That's p e to the t. So this is m prime of t. Then m prime of 0 is n. E to the 0 is a 1. So that's e to the 0 is a 1. And notice that becomes pretty, the p and the 1, this translates to n times 1 times p, which is np, which is in fact the expectation. However, I want to do this from first principles. So let's try to do this without the moment generating function. Now the moment generating function made it pretty easy. But let's say we don't know about the moment generating function. All right. And this is going to be here somewhere. Okay. Let's calculate this directly. And the reason I want to do this is this gives you a nice little combinatorial thing. This is going to be the sum of y equals 0 to n of y p to the y equals y equals 0 to n y. We're going to have now here n choose y, p to the y, 1 minus p to the n minus y. Okay, let's box this up here. Now this is a nice combinatorial trick that I think is somewhat underrated. let's look at this carefully. Let's break this down here. Let's break this down as y. Let's break this down as n factorial, y factorial, n minus y factorial, p to the y, 1 minus p to the n minus y. Now I'm going to do some serious manipulation with this thing here. And it's a beautiful little algebraic result. Notice this y here has this factor. So what I'm going to do is I'm going to rewrite this very carefully. I want to write this part right here. I want to write this as an n minus 1 factorial times an n. In fact, what I'm going to do is I'm going to write that n in a different color so you can see that. I have this y here. In fact, now here's what I want to do in the denominator. The y factorial, I'm going to write that as a y minus 1 factorial. So the y factorial becomes this. Now you can see how that's going to cancel this, right? Now watch this trick here. I have this n, and I'm going to take 1 away. I'm going to take this y. To compensate for subtracting a 1, I'm going to add a 1. But the way I'm going to add a 1 is that I'm going to subtract a negative 1 like so. So I subtracted a 1 and added a 1, so I have not changed this. Now, finally, I want to take 1 factor of p out of here. I'm going to write this as p to the y minus 1. And the rest of it, I'm not going to change. Well, yes, I am going to change it just a little bit. I'm going to change this as 1 minus p. Now, let's look at the exponent. I'm going to do the same trick again. Right here. I'm going to write this n as an n minus 1, subtract y minus 1. Now, notice I'm subtracting a 1, then I'm adding it right back, so I have not changed this factor here at all. What I've done is this n is constant with every term here, so I can factor that out. This p is constant with every term. I can factor that out. And you can see probably what's going to happen here. It's really quite a lovely little thing, a lovely little result right here. I'm now going to, I'll use a blue slash here. I'm going to cancel these, right? And the n and the p, which occur with every single factor, I can factor out. So I now have an np. Oh, and by the way, when I started adding at 0 here, the first term is a 0, so I could have just, what I should have done, and I'll go ahead and do this. This can start at 1 now because the very first term was a 0. When I turn this, when I put this y here, y equals 0 eliminates that first term. So I can start that as a 1. So I think I'll go ahead and make that correction here. Now I'm going to do this. I'm going to start this at y equals 1 to n. The n, I have an n minus 1 factorial, a y minus 1 factorial, an n minus 1 minus y minus 1 factorial, p to the y minus 1, 1 minus p to the n minus 1 minus y minus 1. Whoops, I got a little enthusiastic there, so I better put my negative there. Do a little erasing here. Okay, now you can see what's going to happen. Now, what I'm going to do next, I might do this in green here, is I'm going to let x equal y minus 1. Now, why does that work? Well, then, if y is 1, x is 0. And if y is n, x is n minus 1. So this whole thing becomes np summation x equals 0 to n minus 1. This is now n minus 1 choose x, because that's an x, and that's at n minus 1 minus x. That's p to the x, 1 minus p to the n minus 1 minus x, because that's an x also. And you can see what happened here. This now is just a sum of the binomial probabilities. Where x is between 0, 1, 2, all the way up to n minus 1. With p as the other parameter. And we know that when you sum the binomial probabilities, that's equal to n times p times 1. So the expectation, which is the mean, is equal to np. Okay, so far so good. So the next question is, what about the variance? Well, here it's easier to calculate the expectation of y times y minus 1, which turns out to be the expectation of y squared minus y, which is the expectation of y squared minus the expectation of y. And then this becomes somewhat easy. Then the variance, which is equal to this, well, we see that this expectation of, we know that the expectation of y squared is the expectation of y minus 1 plus expectation of y. So this is going to be the expectation of y minus 1 plus the expectation of y minus, oops, I forgot the square here, minus expectation of y squared. So the bottom line is that we already know, we know this, we need to calculate this and we'll be done. Now you might say, well, why do I want to calculate the expectation of y times y minus 1? Well, let's do that and you'll see why I'm choosing that. Because if you sum this up from y equals 0 to n, we'll now have a y. We'll now have a y minus 1. And by the same shenanigans we did before, we have an n factorial divided by y factorial, n minus y factorial, p to the y, 1 minus p to the n minus y. Now we do the same adjusting that we did previously. This y times y minus 1 is going to cancel some stuff here. Let's see what. And I'm going to write that in red so you can really see the cancellation here, or maroon or whatever color that is. We have a y minus 1. Now let's work on this right here. Well, it looks like we're going to be going down 2 units. So I'm going to go ahead and multiply this as an n minus 1, n minus 2 factorial. This bottom here, it's going to be a y a y minus 1, a y minus 2 factorial. Now let's do the same shenanigans here. I'm going to take 2 away from n and subtract from that y minus 2 factorial. And notice I haven't changed a thing here. And notice it's really the same old, same old. And I'm trying to see where that dot is so I can expand this a little bit. You always end up writing a lot. And let's see here. So we have that. Now this p I'm going to write this as p to the y minus 2 p squared. Then I'm going to do with the 1 minus p. I'm going to do the same thing I did before. I'm going to write that as, and that's such a nice little tidbit here, n minus 2 minus y minus 2. Now that we did all this, we can now factor a lot of stuff out. First of all, let's do some cancellation. These cancel like so. These can get factored out of every term. That can get factored out of every term. So I get an n minus 1 p squared. So I factor that all out. Now I have a sum. Now notice where this starts. Y equals 0, that's a 0. Y equals 1, that's a 0. So this starts at y equals 2. And it goes to n. Now I have an n minus 2 factorial, y minus 2 factorial, n minus 2 minus y minus 2 factorial, p to the y minus 2, 1 minus p, n minus 2 minus y minus 2. Now we do the same thing we did before. What we do is we let x equal y minus 2. Then where y is 2, x is 0. And where y is n, x is n minus 2. So this whole thing is equal to n minus 1, p squared, summation, x equals 0 to n minus 2. This is n minus 2, choose x, p to the x, 1 minus p to the n minus 2 minus x. See, same old, same old. This is now a sum of probabilities. Binomial n minus 1 and n minus 2 and p. So that sums to 1. So we get this expectation of y minus 1 is n minus 1 p squared. Now the coup de grace. What we're going to do here is now we're going to sum that, add the expectation of y and subtract this and subtract this. So I'm not going to use this formula up here for the variance. But variance is going to be expectation of y minus 1. Then I forget so easily. So then that's going to be add that right here, plus expectation of y minus expectation of y squared. So this is, we just said this is equal to n minus 1 p squared plus n p, that's the expectation of y, minus n squared p squared. That's that. Well, if we expand this out, this is n squared p squared minus n p squared plus n p minus n squared p squared. And notice these cancel. So what's left is NP minus NP squared. Factor out an N and a P, and I get a 1 minus P, or sometimes called NPQ. Sometimes Q is referred to that, which is in fact the variance. So as you can see, the key is in the manipulation, this little thing right here. This little manipulation is the key. So that's a binomial distribution, and thanks for watching.